All right. So just in case that was something messed up by me turning off my microphone, I didn't want to, waste a couple hours there. So where we left off is that we ran a test constant, which basically showed that getting the size of a list of any list took O of 1 time, right? And we called this constant time. O of 1. And again, I'm sure if this, if people ever find my YouTube channel and start watching the videos, I'm going to get shouted down about like how bad my understanding of big O is. That's fine because I'm not actually trying to give you guys a good understanding of big O right here. This is kind of meant for that because when you take math concepts 2 or another math class, you're going to learn more about that. Here, I'm just trying to give you a working definition for it, which is that I'm just trying to get you to basically get a good feel of what this feels like. And the idea here is that there's some constant number of operations that happen, irregardless of what the actual size of our input is. If we graph our, if we basically take the size, our n, and graph it against time, so basically here we give a smaller list as our input, here we have a bigger list of an input, even bigger list as an input. The time that's going to take is going to look like this. It's a constant relationship. It doesn't matter what the size is, what our input size n is. The time is going to take, the same amount of time. Maybe there might be some, some jittering if we were like to do a bunch of tests on different sizes just because of the way computers run and just have to handle other stuff in the background, so there's all that kind of stuff that could happen, but it's going to be constant, and we can expect basically a constant amount of time. We are going to contrast this with what we called linear time, which was O of n time. And O of n time meant that basically we have a linear relationship between the size and the amount of time it took. So it might look like this. The relationship between that might look like this. That's still a linear line, right? The idea is that maybe if I multiply it by 10, it goes up only by, so if my input size goes up by 10, by a factor of 10, maybe it only goes up by a factor of 5 over here. So maybe it's like, it goes by, 1/2 n. Or maybe if my input size goes up by 10, this goes up, the amount of time it takes goes up by 20. So in other words, basically everything I add at 2 steps as opposed to 1 step, So, but that's just, that still describes a linear relationship. Now, let's go ahead and take a look at what I find is the easiest linear relationship to explain. Now, when we do big O analysis, because we are eternal pessimists, or you should be at this point, right? Because we know that nothing is going to work as expected and nothing's ever going to run, the way we want it to, right? We can rely on that nothing will go right. That we never really want to take, so as a result, we never ever take into account the best case scenario. Okay, we never ever take into account us getting likely, except when we are explicitly looking at that. So instead, we're going to look at 2 cases when we analyze big O, which is worst case scenarios and average case scenarios. Okay, so and right now I'm going to focus on worst case scenarios because that's easy to understand. Okay, so here we had written a search algorithm, which was we're going to search this array list for this item, okay, and we're going to return the index that it's stored at. If we can't find it, we return -1. Otherwise, for each item, we're going to look at each item sequentially. We're going to go through the list, okay, and if we find that item, we return I. Otherwise, we return -1. So down here on the main method, what I had done is that I created a list of, I think that's a lot of items right now, right? And I'll do 100,000 items. And so we're just going to add, 100,000 items to the list. And what we're going to do is that we're going to look for the number -13 in that list, right? So I'm adding the number 0, 1, 2, 3, 4, 5, through the list. But none of those are -13. So this is kind of a worst case scenario, us looking through a list of a bunch of numbers and the number isn't actually in there. So we run it and it shouldn't take much time. It took 2 milliseconds to run. Let's run it again. 1 millisecond this time, 2, 1, for, this is, you might say, okay, so sometimes it goes twice as bad, sometimes it goes half, sometimes it's twice as good, right? But in the end of the day, what this is really telling us is that basically milliseconds don't really matter too much, right? So in other words, our sample size is too small. The looking through everything operation is actually a very quick operation. So, 27, and now we're approaching this the point where basically just adding these things to the list is going to be expensive. So, like this is 100 million items? So that will actually take a while because it's just going to take so long to populate the list. But the actual searching through it, that went up by a factor of 10 there, I believe. And I mean, so there you go. That multiplied by a factor of 10 by increasing this by a factor of 10, went up by a factor of 10. By decreasing it by a factor of 10, it went down by a factor of 10. To just make sure that this is not, just a kind of anomaly, I'm going to actually artificially slow this down. Okay, I'm going to artificially slow this down by adding in a nested for loop. Now, you may go, wait, you said earlier that having a nested for loop would make this n squared, right? I said that, right? But the rule for that is that only if we iterate over everything in it, right? So this for loop goes over everything in the list, right? It goes through all the indices in the list. This other for loop that I'm going to create over here, this is going to run a constant number of times. It's going to run the exact same number of times no matter what. So watch. Int j is equal to 0. J is less than 1,000. J plus plus, and I'll just increase that if I need to for drama purposes. So ever notice how when you're printing out something, basically if you're like doing a big operation and you're printing out stuff, the program will run slow, but when you don't print out something and instead you just print out your final answer as opposed to just printing out stuff step by step, it actually goes very quick when you're not printing out stuff. If you have ever done that before, hopefully you have. And if you haven't, you'll soon see it. But essentially, printing takes time. It takes an annoying amount of time to print stuff. So so here I'm just printing out. I'm not print linning because that would be a bit obnoxious. But instead, I'm just printing out a bunch of empty strings. And this is just simply going to eat up time. So essentially, what this is doing is that basically for every item in the list, for each item in the list, I do 1,000 print line operations. And then I get it, and then I check if it's equal to something. So that's about 1,002 operations. So we'd say like the big O of this is so that the amount of time this algorithm takes is T of n is the amount of time it takes. And what we're going to do, and what we do with big O is that we turn this T of n into an O of n time, which is a big O time, which is a lot easier to deal with. And a lot of times we can even just skip this whole T of n thing and just directly state what the big O is. But the T of n now of this function is we have to do 1,002 things for each item in the list. That makes sense? Right? So let's go ahead, and this should hopefully sufficiently slow it down so we can see the linear relationship just happen. So I'm going to start with a smaller size, maybe like 10,000, run it. So yeah, so that sufficiently slowed it down. So that took 0.6 seconds. Whoops. This going down to 1,000, that took chopped the 0 off that. And multiplying by that 100, this should take around 6 to 8 seconds to run. So I'm just going to fill out my time by just blandly talking about nothing in particular. Awesome. Good timing on that, too. 6.5 seconds. Okay. So, and it would go for basically a full minute if I were to increase this by 10. So that's just simply to show you that there's a linear relationship. Now, it doesn't matter, saying that there's an O of n time, it doesn't matter if this loop is in there or not, right? What we care about is how fast this grows. We're not like, that's what we talk about when we talk about time efficiency. By adding one more item, how fast does this grow? And linear time, yeah, that's a reasonable amount of time for something to take. If you add one more thing to do, you would, if I'm grading papers, right? If I'm grading papers and I've got to grade 30 papers, that's going to take a certain amount of time. And if you give me another section, which is another 30 students, you'd expect that to basically just double the amount of time of work I'd have to do. Each of those papers, that's a tedious task to handle, but whatever, right? And So the other thing, so that's the other time we're looking at right now, which is linear time. So how do I get from this over here to the big O, right? How do I figure out what the big O of this is? How do I get from this to O of n? Okay, it's actually fairly easy to do. How do I take some t of n and turn it into an O of n time? And we'll go into detail on this in the slides a bit more. But there's basically two rules. First, only the highest order n matters. So if I've got something that takes like 1002 n for our previous example, and then once this is done, right, maybe it takes like 3 operations at the end to stop. Well, this thing over here silently has n to the 0th power, which I'm just going to put there for completeness sake. So I look at which n has the biggest power. And this one does, right? This one has the biggest power. So I throw out everything that's smaller than it, okay? I'm simplifying the rules over here because it also gets the question, you know, we have to ask ourselves what happens when we get into logarithms and exponential times. But right now, we just throw out the smallest power, okay? Once that is done, throw out all the constants that are attached to this. And that's all you have to do to basically transform. It's some of the easiest math you will ever have to do in this degree. Now, there are formal things you do. I oversimplify actually a lot over there. Because there's actually a theorem called the master theorem, which makes it sound super important because it is. But that's taught in 3223, which tells you for any t of n time, any t of n, what you can take that and turn it into the big O notation. So that's taught in 3223. It's a nice piece of math right there, but again, what we're concerning ourselves with, because we only learn what we need to as it comes up, right? We're not going to learn about logarithmic time right now. We're only going to learn about constant time, linear time, and now quadratic time, because that one is because a lot of the algorithms you're writing for homework are quadratic time algorithms. Okay? So, what is a quadratic? So I'm going to go with one of our examples, one of my favorite examples for quadratic time algorithms, something you've probably learned in 1068, and I'm going to scare you a bit with just a bit of verbiage first, but there's nothing too scary about this. T extends comparable T, right? That looks scary as heck, but don't worry about it. Void bubble sort. Bubble sort. We're going to go over bubble sort. How many of you haven't gone over bubble sort before? Okay, a couple of you. So that's fine. That's fine. Bubble sort is typically your first sorting algorithm. It's not a bad one. It's not terrible. It's not selection sort, which is utterly terrible. But bubble sort is actually pretty good for learning purposes here, because you can write both an unoptimized version, a slightly more optimized version, and a much more optimized version. But all of those versions are quadratic time algorithms, which means for each of the n items, in order to sort them using bubble sort, we'll have to do n steps. So this will take in a list of t items, and that's about it. So what the heck is this over here, the t extends comparable t? Well, this is a way of me saying that basically every single, right, this is a list of t's, okay? We'll go ahead and turn this into an array list, since apparently I didn't import list. So this is an array list of t's, okay? Everybody cool with that idea, at least. This is an array list of t's, okay? Here we declare, here we've been declaring what is t. What the heck is it? But there's more to that. First off, if there were more than one generic for some reason, I could use, declare more than one generic there, separated by commas. We'll get into that when we do hash tables more than anything else. But not too scary it's not too scary, and it's not really necessary now. This t extends comparable t over here, though, that looks scary, but it's not really that scary. Because what we have to do when we declare generic is the power to declare more information about it than just that what the letter is going to be. We already know that every generic is going to be an object over here. So we can add a bit of more of information here. Here we can say that this algorithm will only take in, this method will only take in a list of t's if the t's are comparable. Okay, if the t's are comparable. Now that begs the question of what the heck is comparable, but I could make this that basically this only takes in t's that are subclasses of something else. I could say that this is only takes in things that are subclasses of, to use our example from another thing, shapes. Right? Remember our shape object from a couple methods ago? This would basically say that our array list could only be made up of shapes. Don't care what the shapes are, what particular shape it's made up of. Could be an array list of shapes. It could be an array list of triangles, or it could be an array list of circles. Don't care. Okay? So this is saying that this is an array list of comparable, and you won't really have to write this, anytime soon on your own. I'm explaining it because I don't really, at this point, I'm not a big believer in black magic. Okay? We have to use black magic in 1068, like what the heck is public stack void main. We'll explain it later in 1068. Here, though, no reason for black magic. So what the heck is comparable? Comparable is an interface, and it is the easiest interface out there and one of the most useful. What it is that it is a interface of that implements one, that if you implement it, you implement one method, compare to. Okay, so let's see what compare to does. By the way, I should probably explain the objective of comparable first. Comparable is the default way you compare stuff in Java. It's basically saying if these things can be put in an order, you should implement the comparable interface. So integers, as would make sense, they are comparable objects. So integer I is equal to 5, integer j, actually let's go with x and y. Integer x is equal to 5, integer y is equal to 7, right? So we've got 5 and 7. Okay, and the comparable interface says, please implement the one method, which is compare to. Not compare to. So that way you can remind yourself that it's got an uppercase in there. Otherwise, we pronounce it compare to. So it's compare to with a 2 in the uppercase. And what you do is you compare it to any other object, typically itself. So x.compare to y, and it returns an integer of all things. Okay? Okay. System.println x.compare to y. -1. That may not make sense for right now, but it may make sense in just a second. Now if I change them, they were 5 and 7. Now I'm saying 7 compared to 7. That's going to return 0. And then 10 compared to 7 is going to return 1. Okay? So what compare to does is that it says that I will return, is that these things are in order. And if x is less than y, I will return a -1 number. Or another way to think of it, if x comes before y in the ordering you have set up, I'm going to return a negative number. It doesn't have to be -1. It just has to be a negative value. I'll return a negative number. If they're equal to each other, like the dot equals method equal, or they're equal in value somehow, then I'm going to return 0, okay? Because I can't figure out which order they should be in. And if x over here is greater than y, I'm going to return a positive number. Okay, and you might be asking, okay, why don't we use greater than or less than? Well, because this expands, because greater than and less than, they only work on numbers, and we can use this for stuff other than numbers, which is fantastic. For instance, strings have orders. String x and y, they have an order to them. Right? They have alphabetical ordering. X in this case comes, which is ABC, that comes before DEF. So that's going to return -3, a negative number. Okay? Weird. I don't precisely know what the rule for strings is, but if I do y compared to x, reverse that order, it will return a positive number because DEF comes after ABC. So it returns a positive number if it comes after. Okay, so that's pretty nice. And if they're the same value, they'll return 0. So -1 if it's less than or comes before. Sorry, negative value if it's less than or comes before. Positive value if it's greater than. So this allows me to take in basically anything that I can sort, which is nice. So this can sort. This bubble sort will be able to. It's one method, and this is where the power of generics really comes in handy. It's one method that will sort doubles, arrays. So it will sort doubles. It will sort integers. It will sort characters. It will sort strings. It will sort anything that can be sorted. That's really nice, right? I don't have to write a whole bunch of. I don't have to write a bubble sort double array of doubles. I don't have to write a bubble sort array of integers. I just have one method that will sort any array list of anything. That's really awesome. It really reduces the amount of work I have to do, although it does increase, the whole terror factor for just a second. Okay, so let's go ahead and write bubble sort. First, though, I should probably explain how bubble sort works. Okay, bubble sort isn't exactly the hardest algorithm to understand, which is why it's very popular as a starting algorithm. So the objective of sorting is to put numbers in order from the lowest to the biggest. This is, kind of stating the obvious, but it's just important to remember that. So everything should end up in order, and the 1 should end up at the beginning, and the 8 should end up at the end, and everything in between them should be in order. Now, the way bubble sort works, it's named so because as we run this algorithm, the bigger number, the 8, will bubble to the top, and then the 7 will bubble up to the second highest spot, and then the 5 will bubble up to the third highest spot, and so on and so forth. Each iteration of the algorithm, the biggest unsorted number is going to bubble to the top. Okay, and I'm going to just go with the unoptimized version of the algorithm, which simply says that each iteration works like this. I'm going to do this a certain number of times. I'll tell you how many times I have to do this. But each iteration of the algorithm works like this. I compare every single pair of numbers. Okay? Adjacent pair, not like, like every possible pair, but like every adjacent pair. So 7 and 1, I compare them. And if they're out of order, with respect to each other, I swap them. So 1 and 7 are out of order, so I swap them. 1 and 7 are out of order, so I swap them. So then I move on to the next pair. 7 and 8. They are in order, so I don't swap them. 8 and 2 are out of order, so I swap them. Right? They're out of order with respect to each other. 8 and 5 are out of order, so I swap them. And 8 and 4 are out of order, so I swap them. And that's an iteration of bubble sort. Okay? And what happens is that basically that the biggest number, whenever you do this, will always bubble to the top. So I've done it once. The first one number is guaranteed to be in place, right? If I do it again, 2 numbers are guaranteed to be sorted because the 7 will go up over here, right? 1 and 7 don't swap. So here we've got 1, 7, 2, 5, 4, 8. 1 and 7 don't swap. 2 and 7 swap. 5 and 7 swap. 7 and 4 swap, right? And then 7 and 8, it's perfectly happy where it is, right? So you can see that basically that we've got one item sorted, now a second item guaranteed sorted, and right, we don't know about these guys over here. These could have been anything over here, but we do know that guaranteed we've got 1, 2 elements sorted. If we do this a third time, 3 elements will be sorted. And so if we do this n times, where n is the number of elements in here, so 6 times in this example, then we're guaranteed to be done, right? We're guaranteed to be done. So the way this is going to, so I'm going to have 2 for loops. Okay. So the first for loop, for int so I'm going to just use a count over here. For int count is equal to 0, rather than using I and j, because this one's just going to count the number of times that this is going to happen. Count is less than the list dot size. So we're going to run this exactly as the number of times that there are elements in the list. Count plus plus. Okay. What we have to do now is for each pair of items, so for int I is equal to 0, I is less than list dot size minus 1 over here. Why minus 1? Because we're looking at each pair of items, right? So 1 pair, 2 pair, 3 pair, 4 pair, 5 pairs over here with 6 items, right? And if I were trying to go over to the last item, right, and look to the guy to the right, I'd get an out of bounds error. So don't want to do that, right? So this outer loop will run n times, right, where n is the size of the list. This inner loop, the way I'm writing it, will run n minus 1 times. Right? That makes sense to everybody? This outer loop runs n times, this inner loop runs n minus 1 times. This means that the outer loop, for each time it runs, each time this runs, this inner loop is going to run n minus 1 times. So this means that it will run for a grand total of n times n minus 1 times, right? So n times n minus 1, that's n squared minus n. And according to the rules that I was telling you, let's just go ahead and put that on the board. According to those rules, if we've got, you know, squared minus n, we only care about the highest order of magnitude over here, which I'll get into in a second. So we erase this, and so it's n squared. Okay? Okay, so let's go ahead and finish writing bubble sort, which is that if so I'm going to go ahead and just, you know, make this easier to understand rather than making it one big line. T left is equal to, so the left item in the pair, right? The left side of the pair is the one located at I. List.get I, right? The left side of the pair, get I, and the right side of the pair is the one to the right of it, so I plus 1, right? That making sense to everybody? Right, we're looking at pairs of items, the left side of the pair, right side of the pair. Okay, if left dot compare to right, so if we compare the left to the right, if that is greater than 0, in other words, if the left side is bigger than the right side, or if the left side is supposed to come after the right side, that means they're out of order, so we should swap them. So we'll just simply say that list.set index I, so the right should go into index I, and the left should go into I plus 1. Now you'd may be going, why? Normally you need a temp variable to swap these guys, right? Well, these left and rights over here are those temp variables, so don't really need to recreate them. And I normally don't really need, I could just do left.getI.compare to list.get I plus 1, but that would be just a mouthful, especially if I'm trying to make my code easy to understand for you guys. So, all right, so that swaps them. And we'll see that this is actually a quadratic relationship over here. And what that means is that basically if I increase the size, if I double the size of my list that I'm testing this out on, and we need to test this out a bit better, so I'm going to create random integers. So it's equal to new random list.add random.next int. Those are just a bunch of random integers being added. Okay. So if I increase the size of this list, as I was saying, by 2, it's going to go by, if I double the size of the list, it's going to quadruple the amount of time it takes to run. If I multiply the amount of time if I multiply the size of the list by 10, it should take around 100 times slower, 100 times more time. So I'm going to start off with 1,000. Let's list the size 1,000. Takes 18. 10,000. 579. So let's go up again. So if I have 579, you know, it's actually going to take a long time to handle that. What if I go ahead and stop this actually? Instead of multiplying the size by 10, I'm just going to double it. So from 600 milliseconds, let's see what happens to it. So we went from 600 milliseconds to 2100 milliseconds. That's a pretty dramatic increase. That isn't a linear increase in time, right? That's not a simple doubling, right? I doubled the size, and that went up by about 4 times more. So we're looking at, our graph is looking more like this kind of thing, okay? Now, some of you might be going, well, this is unoptimized bubble sort, and I know that a couple of things about bubble sort, such as you don't really, if the last item is sorted, right? If we do bubble sort, right, and this last item over here is sorted, right, then we don't need to actually like check that last item, right? So the first iteration, I need to check all the pairs, right? But for the second iteration, I can leave out that last item. I don't have to check it. And then the time after that, I can check one less item after that. I don't have to check the second to last. So we can stop by just looking at it. So let's go ahead and change that. So basically, the amount of things I have to check decreases by count each time. Okay. Oh, and I should probably, print out the list, system.out.println list, just to make sure it was working, because I accidentally in the morning section, programmed this incorrectly, and it didn't. Why is it? It's not printing out because it's monstrously huge. Right, so let's make sure it prints out. Still not printing out the list. Great. Let's go down to size 100. There we go. So we see that this bottom one is sorted. So it does work. Okay. Just to make sure I'm not pulling the wool over your eyes. But also that's testing the new algorithm, which also shows that the optimized version still sorts stuff. So let's go ahead and check. We were at 21,000 last time, and now it runs in 16,000. And if we half the size, it goes down to 4,000. But that's still a quadratic increase right there. So what's going on, even though we optimized it, right? It should like take half the amount of time. So let's go ahead and actually like count what happens on the board. And I'm actually going to draw a picture. This is one of the few times that I can quote unquote prove, because a mathematician will probably like vomit at the fact that I'm considering this a proof, because it's not. But it gets the point across, which is all I'm trying to do. Okay. So the first time we go through so I think I had like something like 1, 7, 2, 4, 5, and then an 8 somewhere in there. So the first iteration we go through that we check 5 pairs against each other, right? 1, 2, 3, 4, 5, right? So we check these guys, and then 8 bubbles up to the top. Okay. Second iteration, 7 bubbles. We check. 8 will be all the way over here, so we only have to check 1, 2, 3, 4 pairs, right? 1, 2, 3, 4. Okay. Then the next time we have to look at 3 pairs, then 2 pairs, then 1 pair, right? And then the last one, we just say, hey, that's sorted. We're done. Okay, so we don't have to do anything right there. Okay, so not too bad. So now we're going to just steal a bit from Calc 2. How many of you have taken Calc 2? So a number of you. I'm going to steal from Calc 2 for a bit. Let's extend this out. So this was, and let's pretend that basically that this is, and I'm just going to put an extra layer in here just to make it easier for you to understand, right? Okay, so we had 6 items. First iteration took 6. We're just pretending it took 6, then 5, then 4, then 3, then 2, then 1. Okay, now let's extend this to n items, right? The first step will take 1. The last step will take, first iteration will take n steps, right? We're going to compare n minus 1 items to each other. Then second step will be n minus 2 pairs. Second step will be n minus 3, right, and so on and so forth until we get 5 plus 4 plus 3 plus 2 plus 1. Does this sequence remind you of anything? I mean, it's a bit easier if I just simply flip it around for those of you who have taken Calc 2, right? Let me go ahead and flip this sequence around for you. How many of you remember the sequence from Calc 2? It needs a bit of one last thing added to it to fully remind you, I think, which is a plus n over there. Now what do you know what it is? It's a summation. This is one of those well-known equations. 1 plus 2 plus 3 plus 4 all the way up to n is n. Yep, times n plus 1 over 2. Right, which makes a kind of sense because with what I was drawing earlier. I'll go back to that in just a second. Okay, this n times n plus 1 over 2, right? Let's go ahead and multiply this out. N times n plus 1 over 2, that is, let's say, so let's multiply the n out. That's n squared plus n over 2, and then let's go ahead and break this apart. Distribute this 1/2 squared over 2 plus n, right? So no real hard math was done here. I just simply stated something that existed from Calc 2, and those of you who haven't taken Calc 2, just take my word for it, okay? That this exists. You can actually Google the sequence. So okay, and now let's throw this into big O notation. And according to the big O notation, we would drop the n over 2 because that's smaller than the n squared. Okay, and then we would throw away the 1/2, so we'd get O of n squared. Okay, so this, even with this optimization, this is O of n squared time. So, but why do we not care about the O of n? This is a good time to answer that question. Why do we not care about the O of n? Well, what we care about when we see with big O notation, again, is the growth. And the only way we can really appreciate growth is when numbers get really, really big. Let's talk like maybe to 1 million. That's not actually really, really big, but that gets us the point across here. So if we look at this, if we do 1 million as the input size, that will be 10 to the 6 over here, right? And 10 to the 6 over here, except that's squared, so it would be 10 to the 12. I don't care how big is a million. It's dwarfed by this number as so much to be, it's going to be completely inconsequential. And if we go up to something like, let's say, 10 to the 100th power, right? 10 to the 100th power squared, this one has 100 more zeros than that. This one doesn't even show up in, in significant, so this doesn't even show up in significant figures, right, in terms of the amount of time it's going to take. It's inconsequential compared to this to this number. So that's why we kind of just ignore that extra number. Those smaller factors, they're inconsequential. And going back to this picture, I mean, what I've kind of drawn over here was a triangle, which, again, if you remember, triangles are just half of a square, really. So the amount of time this is going to take is, half of the square. And again, I'm being a bit inexpert with here because we were dealing with, well, actually it's n minus 1, and I said, let's just throw in an extra n here just to make it easier, right? And so I just completely fiddled with the math and broke everything, but that's fine. The entire point is that I'm just trying to show you the concept here, right? And hopefully you get kind of an appreciation of the growth rate here. And even when we try to optimize it like this, even if you're doing 1 plus 2, even though we're doing less work the further we get into it, right? And only the first iteration takes n minus 1 times, and everything else takes a little bit less work. It all eventually goes up to basically an n squared time. All right. So with that, I'm just going to look at this. We're going to go through the slides just to simply talk through that a bit more. Okay. So the slides go through this pretty well, and if you want to review this, I suggest going through the slides yourself. But the idea here is that basically that the point of big O is to allow us to compare these algorithms. So we can write algorithms, and I can say, okay, the algorithm we have here is n squared. This algorithm's O of n time. We should use the O of n algorithm versus the O of n squared, right? Because it's faster. Okay, so again, this is the search algorithm, only they do it with an array instead of array list, so nothing special over here. This one is n times m, and they're checking to see if something's different. I personally prefer, I personally like to go through this example by just kind of writing it on the board a bit differently than they have it up here, right? And if you have, basically, if you have two array, if you're doing two things of two different sizes, and this isn't going to come up much in the class, but it comes up in algorithms. Say you have basically a long list over here of numbers, okay? A really, really long list of numbers, 7, 13, 2, 4, 12, 9, you know, and so on, and so on and so forth, okay? Maybe it goes on like maybe for a couple thousand numbers. And say we have something, and we'll call this one X. And say we have another list over here, Y. That's has a much different size. Maybe it has only 3 numbers, 1, 3, and 100, right? And basically, what we're checking to see is are there any, you know, are any of the numbers here, or any of the numbers in here, right? And to do that, we would just basically say, okay, well, take a look at this first number. Does it match any of these numbers, right? Does 7 match 1, 3, or 100? No, it does not. Does 13 match 1, 3, or 100? No, it does not. Does 2 match 1, 3, or 100? And so on and so forth. So each of these n, so let's say that this x's size is n, right? Each of those n items is going to be checked whatever the size of y is, which we'll call m. Each of these n items will be checked 3 times, right? And it makes sense that basically if I increase this to maybe, you know, to take in another item, 101, that basically we have to do another, you know, that this goes up slightly. So this is this times this amount of work. So that's not going to come up too much here. Again, what we're caring about is the quadratic growth rate and the quadratic growth rate, the linear growth rate, and constant growth rate. Speaking of quadratic growth rate, this should look familiar if you've taken a look at your latest homework. The R-unique function, right? Only they're doing this one for arrays. So here, set public static boolean, checking to see if all the elements in the array are unique. So notice that basically that this one goes over it checks all the items in the array, and for each item in the array, it checks every other item in the array. Well, every one but one of the items, right? It never checks against itself. So this outer one runs n times, this inner one runs n times, so it's n times n times. That makes sense to everybody? And again, I'm completely like obliterating the mathematical definitions here, and not in a good kind of obliteration way. The actual, I'm like being super terrible about it. But I found that basically bringing it down to a lower mathematical level really helps with the understanding of this. Okay, so we can think of big O as a order of magnitude, is the word for that. And the simple way to determine that big O notation is to look at the loops and see if they're nested. And we care about if they're nested and they go over the actual length of the algorithm, right? So this one, of the input. So this one, both the outer loop and the inner loop here, they're both from 0 to the size of the list, or the length of the array, right? As opposed to the one I had wrote earlier, which the inner loop ran a constant number of times. It didn't matter what the size of the list was; it would run the same. The inner loop would run the same amount of time each run of the outer loop. So a single nested loop like that, a single loop would be O of n. A nested loop that both of them worked off of size would be n squared. A nested loop, 3 nested loop, which you should hopefully never have to write for this class, is O of n cubed. A classic example of what is an n cubed algorithm is matrix multiplication. And if you just want to go ahead and think about that later on and think about how that would work, right, with each column and rows, that makes sense. That would be, you know, that basically the naive way to do it is, because there's faster ways to do it, is n cubed. So if we want to kind of use that, we can say that basically, let's consider this program over here, right? We've got a program that has an input size of n. So this first block over here, it's a for loop inside a for loop, and both those for loops run n amount of times. So for each iteration of this outer loop, the inner loop runs n times. So this runs n squared. This one over here runs, and this one over here runs n times. Specifically, it's going to run 5n times because this loop in here has 5 basically simple statements in there, right? So let's call it 5n because this one has one statement and these all have other simple statements. Maybe they're like assignments or they're print lines or something like that. So we have n over here, n squared, 5n, and then we have 25 more statements down here. So we would say that basically this algorithm, if it has n input of size n, it would be n squared plus 5n plus 25. That makes sense to everybody? So now, what we try to do is that we try to basically describe that better in terms of O of n. And what that means is that T of n is equal to the big O of f of n. What is this f of n? Well, that means there's two numbers. There's two magic numbers that we're just going to make up out of nowhere. Okay? Not out of nowhere, but we're going to kind of just make them up. The first is called n naught and c. Remember, n is the input size. So n naught is some other for a sufficiently large input size. N naught is a sufficiently large input size. And then there's c, which is a constant. That's not 0. It's bigger than 0 of that. And then there's a function f of n. And the idea here is that once n is bigger than this n naught, once n is bigger than the sufficient size, then the amount of time this algorithm takes is capped by this function multiplied by a constant. In other words, as n gets sufficiently larger than that n naught, there's some constant c for which the processing time will always be less than or equal to cf of n, which means that the cf of n, this constant times this function, will act as an upper bound on performance. So it's easier, I'm going to skip ahead, and it's just easier to see graphically over here, which says, and we'll work out how we figure this out in a second, but we can see basically that after n is equal to 5, the growth rate for the algorithm we just described, it's capped by 3n. It never will get any worse than 3n squared, right? It's 3n squared. Okay, so the big O, so remember, what we do to calculate the big O is that we just, we only care about that big term over here, the n squared. So we just simply drop the lower ordered terms. We drop 5n and 25 and just keep n squared. And then if that had any constants like a half or 12 or anything like it was multiplied by, you just drop that as well. So how do we figure out that that we show that it's n squared using that formal mathematical definition? Well, 5n. So what we do is that we have to find a constant n naught and c that once n is sufficiently large, that cn squared, which was that f of n inside there, that cn squared will be bigger than n squared plus 5n plus 25. So basically, we're trying to find a point where cn squared is equal to 5n plus 25. And if you work out that math, which I kind of just cheated and showed you the answer earlier, once it gets bigger than 5, 3n squared will be bigger than this number, right? Basically, we're saying that if you've got an n squared an algorithm that looks n squared, even if it's weird and it has some jitter in it, right at the beginning, even if it's weird and it has some jitter, okay, at some point it's going to be dominated by this. Right? Even if you've got like this n squared algorithm and it goes a bit jittery over here, but it clearly looks like a quadratic kind of deal, we can say basically that, at some point, this is going to, we can draw a quadratic line that will basically say, it follows this curve somewhat, close enough to say that we're never going to do worse than that. It's also another way of just saying this, that basically that even if we've got this, right, well, not really another way, but it's in the same group of ideas. Say we've got, right, n squared plus 1000n, right? The reason we don't care about this 1000n over here is because once n gets above 1000, right? Once we get to 1001 over here, this would be 1001 times 1001 versus 1000 times 1001. So for every number above 1000, which sounds like a lot, but you got to remember there are an infinite number of numbers above 1000. This term is going to be bigger than this term, right? Which is why, again, we care about the really big numbers. So what we're going to learn in this class are primarily we're going to focus on these three first, the constant, linear, and quadratic. When we get into recursion, we'll talk about log linear time. And then we're going to talk, when we get into recursion, we're going to talk about logarithmic. And then when we get to sorting, we'll probably do more log linear time and log n, which is actually a really good sorting time. Okay? And here's kind of just a graph of the growth rates for if we were to graph, all these different growth rates. And notice that the exponential time, which is over here, 2 to the nth power, that just kind of just skyrockets up into the stratosphere. That's a terrible time to have. And linear and log linear aren't too different. And logarithmic seems pretty great because even though it grows quickly at first, it just kind of just slows down really quickly too and just doesn't grow at all. So these are really happy places to be. Quadratic, you'd be satisfied with quadratic for a lot of problems. However, it's not necessarily a bad thing to have those exponential. Most of the times it's bad for exponential and factorial growth rates. Factorial means basically the only way to solve it is to do everything, check every single function. Let me go over an example of a factorial algorithm. Okay, an O to the n factorial algorithm. How many of you have heard of the traveling salesperson problem, the TSP? Okay, 1. Okay, that's fine. It's a hard problem. Well, sorry, it's not hard in the sense that it's hard to solve. We know how to solve it. It just takes a lot of freaking time to do so. So suppose you're a traveling salesperson, and this gets into graphs, which are chapter 10, but that's okay. Okay, suppose you're a traveling salesperson, and these are all cities, unimaginatively named cities A, B, C, D, and E, right? Okay. Now, these are all cities that are major hubs, right? Okay, and so the idea here is that these are major airline hubs, so you can fly from this city to that city, any city you can fly to any other city, right? Because when they're major hubs, they're easily accessible from one to another. Okay, but as you know, sometimes flying from A to B is cheap, but flying to A to C is expensive. But B to C is pretty cheap as well. So if I went A to B to C, that's pretty cheap, right? So the idea here is if I'm a traveling salesperson, like a traveling businessman, and I've got to visit clients in all these cities, right? And I kind of want to end up back where I started. I want to figure out what the most optimal route for me to find, is. Now, unfortunately, as it turns out, there is no way to solve this problem without me actually just going ahead and computing every single possible combination to figure out what the lowest cost one is, right? So the first thing I would have to do is I want to calculate the cost. So I'm starting at A. So my first one is to go to B. Right, so assume I'm starting at A. So how much does it cost to go if I go to B, then C, then D, then E, then I would have to check maybe B to D to C to E, and so on and so forth. If you know anything about combinatorics, basically the idea is that I'm starting at A, right? I'm just have to start at A as my first point. That's already chosen for me, so there's no choices to make there. But from there, I have 4 choices to make, right? I can make 1 of 4 possible choices, is what I'm saying. So I could go to B, C, D, or E. So I can choose 1 of 4 cities. And then from there, I can choose 1 of 3 remaining cities. And then from there, I can choose 1 of 2 remaining cities. And then from there, there's only 1 choice left for me, really. So this takes a factorial growth in the amount of time it takes. And, if I added another city, that's going to multiply this by 5, and then another 6, and so on and so forth. And it's just going to get terrible. Right? Up to a certain point, once you get to a certain point, the numbers are bigger than I can store in the computer. Factorial grows quickly. Now, you may think that factorial algorithm is terrible as a result, because here's just an exponential, which isn't even as bad as that. If you have a 2 to the nth algorithm, if 100 inputs take an hour, then increasing the input size by 1 means it takes 2 hours. If you increase it by 5, that raises it by 32 times. And adding 14 items will take 16,384 hours, which is just shy of 2 years. So fortunately, we can use this power for good, which is encryption. And the idea with encryption algorithms is that no code is really unbreakable except for those one-time pads. And this also assumes that you don't go and grab the person who has the keys and go attack their kneecaps, because that will get you to the passwords. But assuming you have only the passwords to work off of, you can crack it. It just takes time. And it will take 2 to the n power time, where n is the number of bits in that key. So 40 is really nothing back when these slides were made. And then, but 100 bits takes a billion times longer than the key length of 40. And if you're really paranoid, which you should be, key length of 256, 512, 1024, those will take a long time to break, Okay, so with that, we can start getting into the, so with that, we've learned enough about our array list to actually, do what we came here to do, which is we can actually analyze the performance of our array list. We can figure out how long of these things are going to take. And if you kind of drifted off and not paying attention anymore, I would pay attention, because I can guarantee you that these are going to be on the quiz that will take, not too long from now. So, and by not too long from now, I mean today. So, I'm pretty much giving you the answers to the quiz. So, hence why the quizzes are participation grades. So, let's go ahead and take a look at analyzing the amount of time each of these operations take. Okay, so let's go to our, my array list over here. So let's look at this. First off, let's do the easy ones, right? Size, that's the constant time algorithm. It takes O of 1 time. Is empty takes O of 1 time. Getting something at a specific index. How long does that take for an array list to do? So getting something, right? The first thing I have to do is a check over here, which is to check if the index is out of bounds, but this takes a constant number of time, right? This is just a simple operation over here. Then getting a piece of data out of an array, that's also a simple operation. So these are, and the returning, that's also simple. So these are just 3 simple operations. So getting something from a list, that's constant time as well. So getting is something from an array list is really quick. What about setting? Same thing, I'm just checking to see if it's out of bounds. I retrieve the item, replace it. So it takes 1 step longer and then I return it. So it takes 1 step longer than getting, right? That's pretty good. So it's also constant. All right. So what about add over here? Well, this just says add it to the end. So let's look at add. Add is where it's going to start getting a bit complicated, okay? So let's go ahead and look at that. So add. So first off, checking to see if it's out of bounds, that's a simple thing to do, right? If the size is equal to capacity, in other words, if we've added an item and it's too big, then we have to reallocate. In other words, if we're out of space, we have to reallocate. So how long does reallocating take? Well, with reallocate, remember, we have to copy, we create a new array, twice the size of the original, and copy all the items over. So we need to copy over n items, and that will take O of n time. So reallocate takes O of n time. So if we're out of room, then it will definitely take O of n time. What about if we're adding it to somewhere that's not the end, right? If I'm adding an item, sometimes it's going to be at the beginning, in which case I have to shift over the n items already there. And I have to shift over n items, so that would mean that shifting takes O of n time if I have to shift everything over. Most of the time it's going to be somewhere in the middle, right? And that means I have to shift over half the items. And sometimes I get lucky and I slap it on the end, right? Which would take no time whatsoever. So there's but worst case scenario, first is, but let's just, because we're eternal pessimists, we got to consider it being the worst case scenario. Worst case scenario is that I am always out of space, so I have to copy all the items over. So that takes O of n time. And then I'm adding it to the front, which means I have to shift n items over as well. So that takes O of n. So that will take O of n time and O of n time, which is 2n, but that's also O of n. And then the store and increasing the operation, those take constant time. So this is an O of n operation over here. This is an O of n operation here. So worst case scenario, add is O of n. Okay. Average case scenario. Average, most of the time, vast majority of the time, I actually have room for stuff, right? Vast majority of the time, I don't have to reallocate. So they don't have to worry about that. But I do have to move n over 2 items over, right? I have to take half the items and shift them over. And O n of 2, sorry, the big O of this number, O of moving, plus some other constant number of operations. Well, we drop the constant, right? And moving half the items is still a linear relationship, so it's going to take O of n time. Occasionally, though, we're going to get lucky, because occasionally this is very quick, which is that because we're just adding it to the end and there's space there, right? So most of the time when we're adding to the end, it's quick. But otherwise, we're in real trouble because it's going to take O of n time. Okay? That makes sense to everybody? It's most of the time when you're adding to the add method, it's going to be O of n time. And we're going to review this when we go over the test, because I love to ask a compare and contrast question when it comes to comparing array lists and linked lists. Love to ask that question. It's a good question. Okay, so what about remove? Well, add and remove are kind of inverses of each other. So if you were just going to predict that it would take O of n time just because adding takes O of n time, then you would be right just on that educated guess. But let's go ahead and just think about it. This checking out of bounds, constant time operation. Saving the old item, constant time operation. Decrementing, constant time operation. And then returning, a constant time operation. Those are all simple operations. So the only thing that's over here is that we have a for loop that has the size as an input to it, right? So that's kind of a hint that this is going to be an O of n operation, right? Worst case scenario, we're removing an item at the beginning of the list, which means we have to shift everything back over to the left, right? Best case scenario, we're removing an item from the end and don't have to move anything over. But again, we don't really care too much about best case scenarios because they don't happen that often. It's the worst case scenarios that happen a whole lot, right? So in this case, the removing is going to generally be somewhere in the middle. We're going to move half the items over, which means it takes n over 2 operations, which is O of n time. Checking if it contains it, well, you have to check every item, so that's going to take O of n time. Contains uses index of, and to find the index of something, we have to check potentially every item, which means we have to do a linear time operation. So let's go ahead and summarize with that. Get and set is what these array lists are really good at. Get and set is what array lists are really good at. If you need to check data that already exists or change data that currently already exists, array lists are the data structure you want to use because it is really hard to beat that constant time. Okay? But if you're adding or removing items, it's going to be O of n time. The exception is if we're adding to the end. That's usually constant time operation. But sometimes it will be a worst case because of reallocation, linear time operation. Sometimes we have to just copy all the items over. Okay. What about, and we can also waste a whole lot of space too, right? If we're just talking about, right, we cared about time, but what about space? Remember, when we reallocate something, we create something twice the size. And if we reallocate, add something, and then we never use that additional space, we've kind of wasted, 100% of the space. Or sorry, about 50% of the space being used, or 100% of the actual space we're using. So get and set are the methods that we have trouble with here. Inserting and removing are the ones we don't. So that's why we have linked lists, because it's going to be the complete opposite for the linked lists. Linked lists are terrible at set and get, changing the stuff that exists in the list and retrieving stuff in the list. But that's okay, because if you're adding or removing from the ends of a linked list, it's going to be a constant time operation, which is pretty cool. So I think that right now is actually surprisingly good time to take a break and to take a quiz. So your quiz password is 141. So it's 141. It's going to be on the it's going to be online on campus. So go ahead and take that, and then I think we'll take you can take the quiz, and I think we'll resume at maybe like 6:50. Okay, and we'll get into linked lists.